So today we keep on going. Last time I think I introduced a little bit about gate, right? Gate in quantum computing, and we said that the gate is a unitary operator. That if you have n qubit input, you will have n qubit output. You will not lose any information. So today we're going to see a few very common qubit gate examples. We'll start very simple with single qubit gate. Okay. First of all, the symbol. Symbol of the gate is usually like this. You have a state, and then you draw a line. It's very similar to lab view. Okay, if you guys know how to use it, and then you just put a gate here, okay, and this is the output. Okay, and people call it quantum circuit. You can call it a quantum version of lab view, whatever works for you. And you have input, and then you have output. Okay, and for classical computing, how many single bit gate do we have for classical computer?
And or
No, that's two
nor.
bit. That's already 2 bit. And requires 2 inputs.
Oh, you have an inverter.
Not inverted.
Yeah, not in a wire.
Yeah, so the only non-trivial one is not, right? 0 equal to 1, and then 1 equal to 0. Actually, there's other 3, okay, which doesn't really make sense. The other one is identity, where you do nothing. The third one is whatever your input is, you go to 0. Okay, it's like you lost the information. Okay, it's not really a gate, but well, it's not a useful gate, but you literally can build this gate. Okay, and then the fourth one is whatever you input, you go to 1. Okay, so and that's classical case. Okay. So now let's think about, there's actually infinite amount of single qubit gate in quantum case. But let's start very simple. Let's say NOT gate. We have NOT gate in classical computer. So what is a NOT gate in quantum computer? So similar to the classical case, you can see what the NOT gate will do is that it takes 0 into 1 and 1 into 0. Right? So 0 into 1, 1 into 0. So if you have a state, okay, if you have a state, look like this, alpha. This is a typical single qubit state. The NOT gate after the NOT gate would be you just switch 0 and 1. And this might look weird, but because we didn't say anything about spin, but the symbol for NOT gate is X. Okay. X. It's actually related to X matrix for speed. So the natural question would be, well, we know that to apply a NOT gate, what you do is that you apply a unitary operator onto the state, and then you make the state into, the opposite of what it is, right? So for any for any gate, the question you want to ask is that what is the matrix for this gate? Right, you want to, because you can write down 0 as 1, 0. Right, you can always write down your qubit, the basis, as a vector. Then this unitary operator naturally will become a matrix. So what is a matrix? That's always the question you have to ask when you look at a gate. So first, you need to kind of decide the size of the matrix. A matrix can be n by n, right? In general, you have a size of the matrix.
I have a question.
Yes.
In your qubit, does the the gates 0 and 1 have to comprise a basis of your system?
You have some freedom to choose your basis.
Yeah. So if it wasn't two variables, say it was 3 different states, like a ground state, the first excited state, and you would need 3 different. You need 3. Do you need a basis? Huh?
There's no NOT gate. There's a permutation gate. Right? You change 0 to 1, 1 to 2, 2 to 0.
Yeah.
Yeah. So yeah, indeed. If your system is different, then your gate is different.
Okay.
Yeah. But in general, because people want to, well, information is encoded in binary, right?
Yeah.
So you choose 0 and 1. And that's the only way to talk with computer science people. Well, I shouldn't say that on camera. Anyway. Okay, so what you will find is, let's say the matrix, let's say X matrix, act on a state goes into another state. This state is 1 by 2. Right? This state is also 1 by 2. Right? So you can easily figure out that the matrix here must be 2 by 2. Right? So 2 by 2 multiply this will give you 1 by 2. So we know this is 2 by 2, and then you can write down the matrix components. Right, it's x1, 1, 1, 2, 2, 1, 2, 2. Right, it's the elements in your matrix. And then you can write down your input state. One, write it into a vector form. Alpha 1, 0 plus theta 0, 1. This is alpha beta. And then of course after the NOT gate, you get into this state. Beta alpha. So now you can acquire two. You can get this equation here. So this is a common way to figure out what the matrix of the gate is, and then you get x1, 1, x1, 2. And you multiply this side, you get x1 alpha plus 1 beta. Take first row for column. 2, 1 alpha plus 2 beta. So this is now a vector. Okay, a vector equal to a vector, so their components must equal to each other. Okay. So you have x11 alpha. 1, 2, 3. And you move beta to the right, you know, you move beta to the right, you move alpha to the left. Oh, yeah. You get you get this equation. Now, there's an interesting thing here is that this equation has to be true regardless what alpha and beta is. Right? You should be able to flip. You should be able to operate your NOT gate on any possible state. Right? On any possible state. And because your gate, when you operate it, you don't know what input it is. So your x, okay, your gate should not be a function of your input state. Okay? So x, all this x should be a number that's not related to alpha and beta. Then how can this equation left side equal to right side? Left side you have something related to alpha, right side you have something related to beta. How can you satisfy this equation and have x11 and 1 minus x? Yes?
They would, x11 would have to be 0 and x12 would have to make the right side 0, so
Yep.
that would be 1.
Yeah, exactly. So this one. So this is the only way to satisfy this. And then for the second equation, you will have x22 equals 1 minus x21 equals 0. So that you will have a matrix that flip 0 and 1 regardless of their input. Yes.
Is every gate in quantum mechanics symmetric?
They're unitary, then. Ooh, wait, what?
So they would-
let's.
Like in a NOT gate, if you take the input and you get the output as NOT, but if you put the output back into the gate, you get the input again.
Yeah, of course, because you're.
Symmetric.
Yeah, you're unitary, right? You.
But is unitary a condition for symmetry?
No, it's simply meaning that you put it in and then you put it back in.
Okay.
No, it's put it in and then you undo it and it always come back to you.
Wouldn't there be either symmetric or anti-symmetric?
Yeah, so-
that's
so-
distribution.
Yeah, so I guess here what we need to do is we define symmetry. What we mean by symmetry. Okay? I think, Daniel, what you mean is that you want to input it and then you input again.
Yeah, no, so you put in an input and then you get the output. If you take
Mhm.
the output and then,
Input again.
yeah.
Then no, the answer is no.
Yeah.
Because what you're doing is you select, right? This
Yeah.
is your output and then you do this.
Uh,
It's not always equal to this.
yeah, but for a NOT gate it works.
Yeah, for the not gate it works.
But not all
No,
of them
no.
works.
In general, what only works is that the gate is reversible.
Mm-hmm.
So you apply a gate, you also apply the reverse of the gate, then you end up doing nothing.
Won't they all have to be either symmetric or anti-symmetric? Because otherwise, because that's like all Hermitian operators.
Yeah, they have to fall into one of the categories.
Or I don't know, maybe not.
I'm not exactly sure. Yeah.
Well, no, never mind. I'm wrong.
Yeah. So the way to think about symmetry, it's kind of,
I'm wrong.
I don't know how you define symmetry of a matrix.
With the on the like the
The diagonals.
Opposite
Yeah, the opposite diagonals.
For
if you
example,
the transpose is equal to the
Yeah, the transpose is equal to the
yeah, it's not, because this one is
con-
Hermitian, and then not,
yeah.
some of the gate is not Hermitian, but this gate happens to be Hermitian because this is the operator for spin in the x direction. So it's actually corresponds to something you can physically measure. So that's why it's Hermitian.
Interesting.
And then that's also a reason why it's called X. Okay, X gate. If you check this X gate, okay, this gate is the same as the Pauli matrix, X matrix. Okay. And you can verify it's unitary, okay, just by doing this.
Yeah.
And something similar will be in the final exam. Okay, give you input and output, and then you figure out the matrix, okay, for this gate. And just to show that we have more than one non-trivial gate, okay, I will show a second one. And this one is actually pretty useful. And you will actually, if you go on the IBM Q Experience website, and then they will actually give you this gate. It's called, I need to learn how to pronounce this, Hadamard. The symbol is quite confusing because it's the same as Hamiltonian. The symbol is also H.
Great.
Okay, so so what this do is that think about the just think about what's special about qubit. Okay, qubit can be superposition, right? That's a key difference between a qubit and a bit. So this Hadamard gate, what it does is that it will turn eigenstate, okay, into superposition. Right? Because why people want to do this? First of all, it's easy to prepare eigenstate. For example, you just measure the energy of the electron in your infinite potential well. It will naturally go to ground state or first excited state, right? Or second excited state. So it's relatively easy to prepare your state in this eigenstate. But then to make use of the quantum computer, you have to do computation in superposition. Otherwise, if you just use this state, then it's the same as a classical computer. So a lot of algorithms actually start with a state, eigenstate, and then at an H gate. Okay, they actually naturally start with that. So this H gate is defined as, if you do this, you go to 0 plus 1. Okay. It's one type of superposition. And then if your state is 1, then after the H gate, it should be 0 minus 1. to record my sound. Okay. Now let's again figure out the matrix for the H gate. And it's again very straightforward. It's a single cubic gate, so it's always 2 by 2. H11, H12, H21, H22. So you have H11, H2. Okay, this is 0 state equals to square root of 2, 1 and 1. Okay, and then you also have your gate operated on 0 and 1. Okay, this is your 1 state equals to 1 minus 1. And then you can have 4 equations out of this, and then you can solve for parameters. And naturally, this one will give you H11 okay. So the H gate is, we usually write it in this way. Okay. You can also check that the H gate, what it does is it put 0 and 1 into superposition state. You can also check that the H gate, what you can do, you also turn your superposition state back to 0 and 1 state. Okay. So now think about this. This is quite useful. If you know the output of your computation can only be in 2 states. One is this, the other is this. All right. Suppose your output of your computation can only be these 2 states. If you measure these states directly, you cannot tell the difference between these 2. Because for the state 1, you have 50% probability of measuring state 0. You also have 50% probability of measuring state 1, right? Because the probability is the coefficient amplitude square. It's the same thing for state 2, right? The probability of having in state 1 is always the square of your amplitude, and your probability of measuring the eigenstate 1 is plus minus right? Plus for state 1, minus for state 2. This one.
It's equal to 1/2 of 1.
Sorry?
It's equal to 1/2, 1 over root.
Oh, yeah, yep. It's also 1/2. Okay, so directly measuring your system does not distinguish these two states. Okay, this is very, very important. It will show up again and again in quantum computing. Do not just measure the state. Okay, it will not work. Okay. Then what should you do, right? What you should do is that you should apply the H gate to your state. Then this one will turn back to 0 state. This one will turn back to 1 state. Okay, we can calculate this. 1, 1, 1, 1/2. Okay, the first one is 1. The second one they cancel is 0. Okay, you can do the same thing. So H psi 2 equals this state. Then what you should do is that you should apply this gate to your state and then do a measurement, right? And then you can tell the difference between these two states. Okay. Yes?
Do the eigenvectors of a gate end up becoming important at all in quantum computation?
I don't think so, because your gate is not Hermite, right? Then your eigenvalue actually can be both real and imaginary. So I don't think there's any physical meaning you can give it to.
There's some foresight that tells us, like, we want to have one of them be negative, one of them to be positive. Is that just to be able to, because I mean, because we've already said that it doesn't change the probabilities whether one of them's, whether the second term's positive or whether it's negative.
Yeah.
But so is that just to like be able to distinguish between like?
So you know, the way to think about this is that the information, okay, classically the information is encoded in the amplitude, right? You have a voltage, low voltage is 0, high voltage is 1. In quantum mechanics, the information can be encoded both in amplitude and phase. So the amplitude here, they are equal to each other, but their phase, one is plus, one is minus, that's pi difference, right? If you have EI phi, right? So they two have a pi difference in phase. So if your information is in amplitude, let's say one is in 0 state, the other is in 1 state, then you should just measure them directly. If your information is in phase, then you have to do this gate again to move them to amplitude. Otherwise, you can't directly just measure the phase. Okay. Let's see. And then there's a quiz we can do. Okay. For example, sometimes, well, to change a state to another state, you don't always create another gate. You can use combination of common gate, because it's easy for us just to write down a matrix, but all of this gate actually are physics operation. Okay, you need to change something, And every gate you create, there is some engineer there has to trick his machine. Okay, so for example, if we want to change this state into this state, right? You want to change the phase by 180 degrees on the second qubit. Of course, you can write a gate to do this. Okay, but there's also another way, because we know that when you apply H gate onto this, it will return this to 0, right? 0. Or let's say it in a different way. We know this gate can come from H gate operated on 1, right? We know this can come from H gate operated on 1. And we know H gate operated on this can go to H on this state, can go to state 0. Also, we know you can use NOT gate to change 0 to 1, right? So you actually don't have to build a specific gate for this. What you can do instead is that you have input like this, and then you first do a H gate. H gate turn it into 0, okay, and then you do a X gate. You change it into 1, and then you do a H gate again. Okay, and the outcome becomes this. Okay, so you can use combination of existing gate to build new gates, and it really depends on the actual physics system your qubit is in. Sometimes it's easy to build H gate, build this 3 gate. Sometimes it's simply easier to flip the phase by 180 degrees. Okay. So there's really no way at this point to tell, is it easier to do this or is it easier to flip the phase?
If you multiplied H, X, and H, you would get the gate.
Yep. If you do, so let me, this is the next point here. Okay, if you have an input, and then you have gate A, B, C, okay, and then you have output. So here is a case where it's very easy to make mistake. Gate A first apply on your state, and then followed by B, and then followed by C. Right? So your state should be, is it this?
Yeah.
No, right? Because C first operated on psi.
You need to flip them.
Yep, you actually need to flip them. Okay. Okay, so this is very easy to make mistake here. This clock is not working, right? Okay. Yeah, it's not ironic that I just give a presentation on how accurate the clock can be, and then this one is off by an hour. So the next part would be, well, the single qubit gate we can go on and on, but it's not really interesting. So I will leave some of the, leave some of the gate into your homework and then some of them into the exam. Okay? And they're relatively easy. It's just a 2x2 matrix. You can't really mess up. Okay? And then let's move on. The next one is 2 qubit gate. So here, in the classical case, there are actually a few of them, right? You have AND gate, you have OR gate, right? But then you can kind of come up with the universal gate. You say this gate plus the other gate can build all the gate. And if you are building a quantum computer of your system, then what you should do is you should also demonstrate this universal gate to show people what to do. So first thing is that we want to clarify notation. Okay, so how should we write down our qubit? So suppose you have a system, qubit A, and then qubit B. We'll make it relatively simple. Okay, a two-level. I think this is either, let's call it atom, energy level of an electron. Okay, suppose the first qubit is in state 0. The second qubit is in state 1. What we write down is that this state, there's several ways to do it. One, this product. It means that these two qubits are just separate. We just write them together. That's it. You have a qubit here. You have a qubit there. They don't have to have any interaction. Right? Simply say these two form a system. Then the first one denote the state of the first qubit, and then the second one denote the state of the second qubit. Mathematically, they correspond to that you have two. Well, I shouldn't go into this, but you have two Hilbert space. Okay. And then also people would like to write it down as just like this. Okay, 0, 1. There, 0 represents the first qubit, 1 represents the second qubit. So previously we know that the basis for a single qubit is 0 and 1, right? 0 is a basis, 1 is another basis. So for 2 qubit, there should be 4 different bases, right? You have the combination of them. You can have both of them in 0 state. You can have the second one in 1 state. You can have there's a common notation here. You can have the first one in 0 state, both in 0 state, both in 1 state, and then the second one in 1 state, the first one in 1 state. Okay, so this is your basis. So the way to express your the way to express the state of your qubits, right? 2 of them now, is that you assign a coefficient to each one of them, and then they form a linear combination. And you have alpha 0, 0 plus alpha 1, 1 plus alpha 0, 1 plus alpha 1, 0. Okay, so this is a way to express your state, because you have 4 bases, then each of them has a probability of showing up in your state, and each of them carry a phase. It's exactly the same thing as you have alpha and beta in a single qubit state. Now, here comes to the second common mistake. A lot of people would do, what they would do is that they will write down their state as, they think, well, the first qubit is in superposition, can be in superposition of 0 and 1, right? So they write down their first state, alpha 1, beta 1. And then the same thing for the second qubit, right? The second qubit can also be in 0 and 1. Okay. Makes a lot of sense, right? Does it work? No idea, right? Well, the way to think about it is that, is this two equivalent?
No.
Well, you have 4 coefficient here. You also have 4 coefficient there. You have the same number of, well, same degree of freedom, right? 4 parameters. Okay.
But if you like combine like the 0 and 1 terms, like in that way, like
Yep. So there's,
we're talking.
So there's a special, well, a special type of state. For example, 0, 0 plus 1, 1. Okay, this state. You can try it. You were never able to figure out these 4 coefficient to satisfy this. Okay. We can give an example here. We can calculate it here. No, it turns out I didn't include the calculation. Oh, I do. Okay. So if you write this up, expand this, you get alpha 1, alpha 2, 0, 0. Okay. And then you have beta 1, beta 2, 1, 1. And then alpha 1, beta 2, 0, 1 plus beta 1, alpha 2, 1, 0. Okay. So for this state to be equal to this state, you will need alpha 1, alpha 2. Okay, this coefficient equals to 1 over square root of 2. You also need beta 1, beta 2. Okay, this one equal to 1 over square root of 2. But this 2 coefficient has to go to 0, right? Because there's no terms here. Okay. This equation actually doesn't have any solution. Why? Because alpha 1 multiply alpha 2 equals a non-zero number, which means alpha 1 and alpha 2 are neither 0. Right? If any one of them are 0, then this will be 0. Same for this. Beta 2 and beta 1 cannot be 0. So if all these 4 cannot be 0, then there's no way that the product here can be 0. So there's simply no solution here. Okay? And this is kind of, if you don't care, then it seems okay, right? But if you do care about this, or if you do understand a little bit of classical computing, you'll kind of be puzzled, right? You have 2 qubits. They each have 2 states. and then you write them together. How would this differ from this? Okay. Yes.
Well, when you wrote that down, you didn't use a normal multiplication operator, so wouldn't it just be that it's a different kind of product than just a
You mean this one?
simple- Yeah.
But when you multiply this, you get this one, right? So when you take 0 here, multiply with 0 here, you can get 0, 0. This one is the same as what you would do in classical computer,
I
right?
meant like you wouldn't that assume that whatever operation that stands for has to work linearly, so you
So
take the sum of two things opposed to just
this is not an operation, it's a notation of writing two qubits together. There's no operation.
I meant
Mhm.
I meant kind of like a mathematical operator like multiplication or integration, not as in like a quantum mechanics type operator.
So here, let's say a little bit clear here. This is not an operator. This is not an operator. It's a way to write down. It's a way to express the state of your qubit. Okay, we say when qubit 1 is in 0, qubit A is in 0 state, qubit 2 is in 1 state, we say we can write down this combination of this state as 0. It looks like a multiplication, and then 1. But in reality, nothing happens. Okay, nothing happens. It's just a notation when you need to write down information of two things. Okay, for example, in classical computing, what you do is you write down two bit, right? You say 0 and 1. That's 1, right? In classical computer, well, in quantum mechanics, what you do is you write down 0, and then you give it a notation here, and then you write down 1. Okay, you simply put them two together. There's no difference here. So very quick here, okay? I blame that clock. So what's the difference here? Is that this state is so-called entanglement. Okay, entanglement. And for this state to form, okay, in order to bring up this state, you need these two qubits to interact with each other, which will not happen in classical computer. You need these two to interact with each other. And what's more important is that, now if you think about it, what's more important is that for this quantum state, information in this quantum state cannot be written down as the classical information. Right? Because classically, you write down the first one and you write down the second one. You write down in this form. But entanglement doesn't allow you to do this. Okay? So there's additional information in entanglement, which you are not able to get if you just measure this qubit individually. You say, well, qubit 1 is in what state, qubit 2 is in what state. Even you know these two information, you still don't know the state. The information is shared between qubit A and qubit B together. And if you don't understand, doesn't matter. We will come back to this later.